In our app, we strive to follow Ben Schneiderman's golden rules of interface design. This is the app's main page. Our Android UI follows our theme of Scooby-Doo. It is built using Java and acts as an interface between a user and our van. With our UI, scanning and connecting Bluetooth devices is straightforward. We follow the rule of easy reversal of actions. If a wrong device is selected, it's simple to reconnect to the correct one. The app also exchanges information with the mystery van in the form of strings. The strings are exchanged with the RPI, which allows us to exchange information from the van.
Our UI creatively incorporates elements of our mystery van, which can be manually controlled with arrow keys. We can set obstacle coordinates by dragging or entering coordinates into the interface. Dragging an obstacle off the screen removes it. Toggling our unique Set and Done button will lock the obstacles in place. This follows the rule of preventing errors, as it prevents obstacles from accidentally being dragged away from their intended locations. In addition, the various different obstacle input methods follow the rule of keeping users in control. Next, we can easily tap obstacles to set their orientation. Obstacle information is sent by clicking on the van image under the grid. To follow the rule of offering informative feedback, a brief toast message is shown once the information is sent. Finally, the toggle button communicates the arena's location to the van, indicating whether it is indoors or outdoors.
The Algo team has developed an algorithm that guides our mystery machine through a maze to capture all the ghosts. Coordinates of the ghosts are sent to our server, and our algorithm calculates the fastest path while avoiding collisions. The algorithm uses dynamic programming to find the optimal path by checking possible routes and calculating costs. For precise navigation, it leverages A-star search, which combines distance with heuristics to guide the machine. Once the best path is found, the algorithm generates commands that tell the machine how to move.
We also developed a time simulation of the mystery machine's movements. This ensures that the machine will stop, even if the task is not completed. With dynamic programming and A-star search, our algorithm effectively guides the mystery machine through complex mazes.
By applying PID control on the motor's PWM, the van accelerated smoothly and achieved accurate straight-line movement. Calibrating and measuring the i.am.shlomo gyro enables accurate orientation detection for precise turning. With the calibration and PID control, the van utilizes its servo motor to steer itself to the desired angle. Combining the use of real-time operating systems and interrupts, the van is able to multitask and respond quickly to external inputs and commands. Commands were designed to enable flexible control over the van's movement.
The van was tuned in coordination with the algorithm's team. With accurate turns and movements, it can move quickly and precisely along the calculated path, setting the foundation for success in Task 1. The ultrasound and IR sensors were used for object detection purposes and to measure the distance of various obstacles. The video demonstrates the purposeful placement of the sensors to maximize their capabilities. The sensors are used to measure the size of the second obstacle to calculate a path back to the car park. The IR also played an important role in determining when to turn using its precise object detection capabilities.
Welcome to the RPI and Image Rec. The Raspberry Pi is the central processor of our multidisciplinary project, serving as the command center that coordinates communication between the various hardware components. It processes and sends data to and from the camera, STM32 microcontroller, Android tablet, and laptop. Due to the limited processing power of the RPi, we rely on calls to a Flask server hosted on a laptop connected to the RPi's Wi-Fi network to perform inference on captured images.
To support our Android and hardware operations, we developed a robust image recognition pipeline that addresses challenges like variable card backgrounds and lighting. We applied 22 different filtering methods to captured images, starting with grayscale conversion, followed by adjustments to highlights, midtones, contrast, and brightness. This approach was inspired by experiments in Adobe Photoshop, where we used value-driven image editing to remove background patterns. Next, our YOLO V9 model, trained on over 8,000 images on 200 epochs, runs inference on each of the 22 processed images. From the 22 results, the best prediction is selected based on the horizontal positioning and size of the bounding box, prioritizing the former. The final recognition results are then sent to the Android tablet for display. For Task 2, we implemented a similar but more time-efficient pipeline with fewer filtering methods. The results directly control movement commands issued by the Raspberry Pi to the STM32 microprocessor.
Run.